Okay, hello and welcome back everybody. I hope your spring break was good. I realize this is technically the second video since spring break, but I had you watch something else that wasn't me for the most recent class. So welcome back to me speaking to you from the online world. We're moving on to chapter 16. This is complex functions and transformations. We're getting through the whole chapter today. It's not a very big chapter. And really all the point of this is saying, hey, you worked with complex numbers. In the last semester, we're going to work with complex valued functions this semester, right? So I just want to be clear, C, I can have like my Z in the complex numbers, which is what you worked with last semester. We can also have f of Z. Okay, so there's a function that takes in a complex number. And, this is maybe equal to zeta or something. I'm bad at drawing zeta. So it outputs a complex number. I'm sure everybody has made the assumption that these functions are perfectly valid by now, but, today we're actually going to be working with them to see maybe a little bit how they actually behave. So something that's really important to use when we talk about these sorts of functions and complex numbers is the polar form representation of a complex numbers. I think you remember, you might have gone through both of these actually, but we want to recall that we can either represent a complex number, complex number as a sum of a purely real, in this case x, and purely imaginary, in this case IY, number. You can either represent it as a sum of those two, and in that sense, this is something like thinking about it as R2 in Cartesian coordinates. You basically want to think about that as your x-axis and that as your y-axis, and then you have some point in R2, or in other words, the complex number is like a vector in R2. Or we want to think about, hey, we can actually represent vectors in R2, represent a vector, and that vector is x comma y in R2 in polar coordinates. And that's the case where we let r equal the square root of x squared plus y squared, and we let theta equal arctan y over x. And then, you could represent that itself as a vector, I guess r comma theta, and you just want to be clever about interpreting that as a polar coordinate vector. Or when we get into complex numbers, we can actually refer to this as a single number, right? The same way that we have an operation of the first vector entry x with the second vector entry y, you have an operation of x plus iy. We can construct the operation with r's and thetas as it's a multiplication of r with e to the I theta. And let's recall really quick that e to the I theta is cosine theta plus I sine theta. This was Euler's identity. And then this starts to make it clear, hence, if I multiply by r, I have r cosine theta. What do you know? That's x in polar plus I r sine theta. What do you know? That's y in polar. So that's why we can get away with representing the same complex number z either as x plus iy or as r e to the I theta. Okay, so when we think about a function now, f of z equals w, so this is now complex, there's a complex input z, a complex output w, we can represent the output of this function as some real output, this is a real function u, and some real function v, if I get rid of the I there, some real function v, and then this is exactly our Cartesian representation of the output of the function. We can also do the same, play the same game where now I can represent the output of my function in polar coordinates where the radius now depends on my complex input z, and my angle theta now depends on my complex input z. And actually, I don't think the book gets into this, but we could almost go one step further and say something like f of r e to the I theta, and this is maybe r input, theta input, now has an output, r output, r e to the I theta of the inputs, e to the I theta output of our input, e to the I theta output, input. And in this setting, it's really like a function on two inputs, and you get two outputs, which makes sense. These complex functions should be functions. Basically, they're kind of like vector fields, because like vector fields, this is almost like it's mapping R2 over here, two inputs, and we're getting R2, two outputs. But we want to then associate those vectors to complex numbers. But that's what we want to think about with complex functions, is really they're kind of like vector fields. They're like, a vector field in R2 to the vector field of R2, but then we reinterpret those R2s as the complex plane instead. And what's nice about that, why is that very useful? It's a very useful way of interpreting these functions because, let's scroll down here, if we interpret this function as a vector field, interpret as a vector field, if we interpret that complex valued function as a vector field, if it's defined as iz, we can interpret the outputs now as the negative imaginary part of z plus I times the real part of z, which if we reinterpret that, if we let z equal x plus I y, then really it's f of x and y, that x and that y, is the negative imaginary part of z, but the imaginary part of z is right there, so it's really negative y, and then plus I times the real part of z, and what's the real part of z? It's right there, plus ix. And if we reinterpret this now as a vector field, we recover negative y is my real component, and x is my imaginary component, and so we can really get away with perceiving complex valued functions as vector fields. In this case, the complex valued function minus imaginary z plus I real part z is really just the vector field minus y x. And we can see that now if I scroll down and we plot some of the vectors here. What is the output of, change my color here, what is the output of f of 1? What we assigned to input is 1 comma 0, right? There's my input. And the output, you'll recall, was negative imaginary plus I real. And so we get negative 0 plus I times 1, which as a vector is the vector 0, 1. And that's the vector we've drawn here. It's the vector pointing up 1 and to the right 0. And we can do that with every single input here. So here's another good input. This is a complex input. The point here is negative 1, negative 1. That's as a real input, or we associate that to the complex, negative 1 plus negative 1i, which is why you can see that there. And what does this output under f? I have the negative imaginary part, which is going to give me a positive 1, plus I times the real part, negative 1, and I associate that to a vector. Now my vector is 1, negative 1, and that is exactly the vector that moves 1 in the right direction and negative 1 in the vertical direction. And so there's my output vector. So this is one way of representing complex valued functions. It's as vector fields, and it's a very useful interpretation of those. And that's if I zoomed out and plotted it as a vector field. This is stuff that we've basically already done in Calc 3, but now we just want to get good at interpreting what is this field saying. This is the real axis. Now this is the imaginary axis. Okay, so that's the only difference, is now we're interpreting the axes as meaning something that they didn't mean before. We're interpreting the axes as a real and imaginary axis instead of just R2, like the x-axis and the y-axis. And the vectors are the output of my functions at each of those points. So if we jump down, kind of the primary reason why we care about these is the wave function. I should say your primary consideration. Mine can be definitely different as a more of a pure mathematician, but definitely as a chemist, your primary consideration for these is the wave function. Wave function in quantum mechanics, QM. Because the wave function in quantum mechanics necessarily needs to be complex valued. We don't really have a good way of representing it not complex valued. And this goes way, way back to just the fact that matrices are allowed to have complex eigenvalues, right? A matrix with purely real inputs can have a complex eigenvalue, and that basically forces forces complex numbers to show up in quantum mechanics, because quantum mechanics is really just based around linear algebra, at least the linear side of quantum mechanics. So since matrices can have complex eigenvalues, even though they're real value matrices, then all of a sudden the eigenfunctions we recover out of them have complex value coefficients, which means that their outputs are complex valued as well, and so we're forced in quantum mechanics to work with complex valued functions. And in fact, the inputs, right, the input there is a real input, so it's a real input, but the output, because these are eigenfunctions, the output has to be complex valued. And so that's what's going to happen for what we see next, is we're going to start to deal with some wave functions. And we'll just talk really quick, I guess, about taking derivatives of these. You can take one-dimensional derivatives of these just like you would traditionally just take the derivative on the real part and the imaginary part. It gets trickier if you represent this in polar coordinates because you're using a product and chain rule here. Okay, so the product rule says taking a derivative of r, I'm going to keep the e to the I theta the same, and then I'm going to move over, take a derivative of e to the I theta, and keep r the same. And we're missing an I here because of the chain rule. But yeah, so that's how we're going to take derivatives in at least complex outputs. The complex, or the input is still real, so our derivative is a purely real input there. We're still allowed to use the fundamental theorem of calculus. Nothing crazy there, so you can feel good about that. And then this next example is interesting because if we represent a function with a real input and a complex output, such as the one we have here, just x plus ix, then what this becomes is this is a line, right? The real number line embedded. Change my color here. Embedded in C, which is a plane. Okay, so the image of a line gets pushed into C. So in other words, it's actually a curve. It's some sort of curve in 2 dimensions, right? You want to think of this as just like the gammas we were considering before. Just like gamma of t in our quote-unquote Calc 3 section. Okay, so it's like gamma of t is now evolving over all of r, and gamma takes values in the complex numbers, but we're going to interpret that as R2 if we plot it. And so what does, this is basically saying the line x, I'm going to move to the right by x, and I'm going to move up by x. Okay, so to the right by some amount and up by some amount, well, that's exactly diagonally up and to the right. And so we recovered the beautiful line, slope 1. This is now, we want to interpret this, right? This is not the x comma f of x plane. That is not what's happening here. This is not like the plot of the function x equals y. This is instead an embedding of the output f of x, which happens to be x plus ix, which is interpreted as a vector x in R2. So I'm embedding this vector xx in R2. And what does the vector xx look like for all values of x? It's exactly the diagonal line. So that's how we're interpreting this complex valued function. Moving on to the idea of wave functions, let's jump back to our classical solution of the Schrodinger equation particle in a box solution. Right, that's why they're calling this wave functions in a box. So this is the solution to your Schrodinger equation in a box of length L with an infinitely large sides. And you actually we have harmonics, right? We have infinitely many solutions indexed by n, and we can actually write any solution as a linear combination of the indexed solutions. So we have these are in some sense are fundamental solutions. They're like the fundamental frequency solutions, and then we can construct any wave function which still satisfies the Schrodinger equation as a linear combination of those. That should just be a throwback to your ODEs section where I'm sure you got into solving the Schrodinger equation. But this is what we want to think about, but let's keep in mind that even though last semester you started talking about these linear combinations as real valued, we are now allowed to have complex valued coefficients here. Okay, so if we put complex valued coefficients, we can still construct a linear combination, and they'll actually all still satisfy the Schrodinger equation. It's actually very important that we do allow ourselves to have complex values there. Now, this brings up a good question, though, is considering if this is complex valued, it is complex valued, how do we, quote unquote, take measurements? That's a great question, because if I'm sitting in a physics lab and I whip out a ruler and I measure the length of the table that I'm working on, I'm going to get a real valued number out of that. And actually, in particular, I'm getting a positive real value number out of that. And so it turns out that the measurements that we take, somehow we still have to transfer complex valued coefficients into some sort of real value, which should correspond with the measurements that I take in the physics lab. And the way we do that is with the following integrals. So we define the norm, and really you can just think about this as this is the magnitude, it's the complex magnitude. We define the norm of our function. That's the same function we had above, right there. The norm of that function is defined as the complex conjugate of the function times the function itself. This is the same stuff that you had in the past with computing norms of complex numbers. So the norm squared is just the conjugate by itself, which is just going to give me the real part squared plus the imaginary part squared. And then to obtain a measurement, I don't always have to compute this, but this is maybe the easiest measurement I can obtain. This says what is the probability that the wave function exists in the interval a to b. So I could say one such measurement is, quote unquote, testing if the particle is in some region of space on my box. So if I isolate my box, I shove my hand in there, and I ask myself the question, did I just run my hand into the particle? The answer in the physics experiment will either be yes or no. But if I repeat that measurement, if I shove my hand in there like 300 times, then the answer will be yes, some probability of the time, proportion of the time, and the answer will be no, another proportion of the time. And if I did that infinitely often, I would find that my probability that my hand is going to run into the particle as I shove it inside the box, if my hand has width b minus a, can be computed by taking the norm of the wave function that represents the path of the particle and squaring it and then computing the integral over that region. So let's actually just perform one of these calculations. It's a little bit ugly, so I wouldn't worry too much about this. So let's just assume these are now eigenfunctions, right? They're orthonormal eigenfunctions, so they have norm 1 under the integral. But let's just assume that our wave function is described as 1 over root 2 times the first eigenfunction plus 1 over root 2 times the second eigenfunction. Those eigenfunctions, if I recall, are just these signs. So I let n equals 1, and then I take 1 over root 2 times that, and then I let n equals 2, and I take 1 over root 2 times that. I'm going to ask myself the question, what is the probability that the particle, where's my box? Here's my box. This is 0, this is L. This is asking, what is the probability particle is in the region 0 to L over 2, which is half of the width of my box. So there's my L over 2 mark. I'm asking myself the probability in there. What's the probability if I shove my hand into the left-hand side of the box? You know, that particle, especially quantum mechanically, is whizzing around. It's almost a cloud, right? The particle is just a cloud over here. It's just sitting in my box. I want to know the probability that I find the particle on the left-hand side if the wave function that actually describes the particle looks like that. Okay, so when I talk about the wave function of the particle looking like that, it turns out that the wave function which describes the particle actually looks something like this. And from there, you can start to ask yourself the question, okay, what's the probability it's on the left? Well, it looks like it's a bit high. If I go through the process of integrating, we get 0.924. So that means 92.4% of the time, if I stick my hand in the left-hand side there, I'm going to run into the particle. And that's really how we make a lot of predictions with quantum mechanics, is with these probability measurements. Okay, so I think that's all I have to say. There's a little bit more to this exercise, but I don't want to get in too much to it because I've spent a lot of your time already. And there's another video I want you to watch for today. So that's all. I'll stop there, and that's all I have. Thanks very much. Bye.